And we're going to do a new document. I'm going to add a, don't save the previous one, save it. We're going to add a lister spreadsheet. And we're going to save this file, save as 4.4 rates of change in an exponential function. Or you could also put your name on it. So when you take a screenshot, I can see your name here. So maybe file save as logos. I'll put my last name. First initial. There you go. And now take a screenshot of that. Turn that in. Okay, let's read. Escape. Let's read what we're doing. And what we're doing is this assignment here. It's a change of exponential model. Score is 50 points plus 10 points for every number of questions submitted correctly. Remember that the parent function for an exponential model is y equals a to b to the x, where b is 1 plus or minus the rate, which we can utilize in this section. So here, we're going to take the exponential function y equals 2 to the x and make this table. And find the first differences and see how y is changing. So let me do that. So this is x, this is y, and the model. Oh, pardon me. Difference 1 and the model. Difference 2 and the model. So this was 0, 1, 2, 3, 4, 5. And we start with 2, and we're doubling it, I believe. Oh, doubling it. Is that what we were doing? 2 to the x. I think that's what that means. So, oops. Sorry about that. Okay. So the formula is explicitly given already. As y equals 2 to the power of the independent variable, which is in column A, so we're going to type A and enter. Okay, it's going to replace that, which is what I had already, except that I started with 2, they start with 1. That's right, I'm not starting at 2, I'm starting at 1 times 2. So this model that has a 1 in here, 1 times. So you're starting at 1, that's your A, and your B is 2. Okay, so what is the first differences here? Well, 1 minus 2 is 1, 2 minus 4 is 2, 4 from 8 is 4, 8 from 16 is 8. So that should be the first differences. But I'm going to go ahead and put menu. It's a data thing, and I want to do a list operation. Menu 37, menu 372, and of B. Enter. So these are the first differences. That is that 1 plus 1 is 2. 2 plus 2 is 4. 4 plus 4 is 8. So 1 plus 1 is 2. 2 plus 2 plus 2 is 4. Plus 4 is 8. Plus 8 is 16. Plus 16 would be 32. And that's the first differences. Now we could check the second differences, but I can already come to a conclusion that apparently they're going to be the same. Right. So let's write that down. Insert some notes. Number 1, 4, 2dx. The first differences is the same geometric sequence. Before I change it to 3, just, interesting, 3 to the power. Let me undo that. Control Z. I'm trying to say it's 1 times 3 to the power of A. Okay? So, if you do 3, well, this is also multiplying by 3, you can tell. So, what if I do something like, B is supposed to be 1 plus something, so times 1 plus 0.10 divided by 12. And I see that those differences is d C2 divided by C1. And that's the same. In fact, I could do them all equals, excuse me, then I could see if they're the same all the way down. Control click and go down. I said control click and go down. Let's see. Can't do this last row, but you see that these are checking out the ratios and the constant ratio. So yeah, it's a geometric sequence. But further, I can say that the first difference is the same geometric sequence. It's not the same geometric sequence because you can see that this sequence is this one, and the first difference is a different sequence, but it's the same, has the same ratio, common ratio. So for f of x equals the first difference is a geometric sequence. So let's put that back. To the power of a. Okay. So this is the ratio. Okay. But the difference, we'll do a second difference. Let's see, menu, data. Out of this time of C. And yeah. But look, when we change it to 3, raise to the A. Okay, so I can conclude. It says is a geometric sequence with the same ratio, common ratio, and possibly let's say and different different starting point, initial value. Number 2. Let's take a look at that. Number 2, new data, and let's put the data in. Let's read. The population for a small town grows as an area of 20% per year. The initial area of the town is 2 kilometers squared. Describe the needs to fix that. Describe the growth rate of the area of this town. Okay. Let's take a look at that. I'm going to insert a new I meant to say spreadsheet. Let's say delete one. Go over to that and make sure I'm top of that particular one. Then press delete and get rid of that page. I want to go to this page. I want to insert another spreadsheet. This time it's X. And this time, or it could be X, where X is the number of years. And this is going to be area, town area, square kilometers. And if I remember correctly, and starts at also starts at 0, 1 through 5, but it's 2.4, and then 2.88, and then 2.456, then 41, 4, 1472, and 49766, 49766, 9766, 49766, 4. So that's the area. Now, you take a look at the shape. But I don't have to really take a look at that shape. You told me that the percent growth is rate, so I know my model. The model should be let's take a look. I'll put the model here. I started with 2 and times. You told me 1 plus 20%, so that's 20 divided by 100. And there you go. But let's put a decimal, so instead of a fraction, so it gets rid of the fractions. 20% can be written as 1 plus 0.20. So what's 12 divided by 5? Oh, but 2.4. That's the next one because I just did the model to 1. Let's increase that and do it for every x. So to the power of x, which is in column A. So to the power of A, press enter. Override it, go ahead. And sure enough, that matches. And now, I can now extend my model all the way down to where it needs to go. So recursively, this would equal B7 would be B6 times open parentheses 1 plus 0.20 or 1 or times 1.2, and recursively this would be equal to A6 plus 1. And now I can shift and highlight this. If you read the rest of this, you would see that they would want me to do this for whoops, 70 years. So let's do that. Shift. Okay. And I need to do Control Shift. Control Shift. I guess not. Let's see. let's see. Let me pause this. Technical difficulty here. So let's highlight these two cells with shift and go over, and then now do control click. Let's try that again. Shift, go over, control click, go down. And it said to go 70 years. So is that 70 or 71? Don't remember. I'm just going to go to 71. And I was asked to fill this according to number 3 to 70 years. Oops, went a little far. Of course, I have the model, so why? Well, this is what it would be recursively. Years since it started growing. So year 0, 0x is the years since. So 70 years since it is now that much, and matches the model. That much area, kilometers squared. And to look at that, we could look at the insert this graph where this is x, it's the town and area. So there's the shape of the scatter plot. Then I can show regression exponential, which matches what we said. It started with an area of 2 kilometers squared, is growing at a rate of 1.2 kilometers times 1.2 kilometers per year. Okay. Let's write the conclusion down here. So 2, the area, the town's area is growing at a rate of 20% per year. The exponentially. Well, we could also say 120%. Exponentially at a rate of 20%. The next year's area is 120% that of the previous years. So we can characterize it. The question was, it shows the growth of the town. So we use a table to describe the rates of growth for this town. So using a table, of course, D1. Oh, that's not the same D1, right? I think the D1 and 1 are the same. DT. That's menu, data. Escape the menu, data. B. So those are the differences, which should also have a rate of 1.2. Right? 2 divided by D1. Yeah. So let's take a look at 3. Use a spreadsheet to generate 70 years of growth. When using Excel, you can do this recursively. But what if you have limited space? This would be part 2. It's a separate video. Okay, so